Class 11th Chemistry, Unit 5, States of Matter, and in this video we will discuss about van der Waals equation and compressibility factor. First come to van der Waals equation. In the previous video we have discussed that real gases do not follow ideal gas equation at all conditions of temperature and pressure. So, ideal gas equation is corrected for real gases. Corrected gas equation applicable for real gases is known as van der Waals equation. Now, first we will discuss the correction in pressure term. At high pressure, molecules do not strike the walls of the container with full impact because there is a attraction interactions are working at high pressure. So these are dragged back by other molecules due to molecular attractive forces. This affects the pressure exerted by the molecules on the walls of the container. Thus, the pressure exerted by the gas is lower than the pressure exerted by the ideal gas. You can see in this diagram the molecules which are striking to walls of the container like this. Okay, this will attract or this will feel the net inward pull this side. That's why this molecule will not strike the walls of the container with full impact. That's why the pressure exerted by the real gas is smaller, and to make it equal we have to add one correction term, and this is the correction term, an square divided by v square. Okay, and when we add this in pressure exerted by the real gas, that is observed pressure of real gas, then this will be equal to pressure like ideal gas. Now, correction in volume term. Again we have discussed that at pressure is high, the actual volume occupied by the gas molecule cannot be neglected compared to volume occupied by gas. Okay, the volume occupied by the molecules also become significant because instead of moving in volumes V, these are now restricted to volume V minus NB, where NB is approximately the total volume occupied by the molecules themselves. See in this diagram, according to kinetic theory, this whole space available for the molecules to move around in, because the actual volume of gas particle is negligible. But in practice, in fact, only this amount is available because the rest is taken up by the molecules themselves. This space, which is the actual volume of the gas molecule, is not available for the molecules to move around in. Okay, that's why this is the correction term in the volume. And if we apply these two corrections, that is correction for pressure and volume, we will get the new equation, this P plus an square divided by v square, and this is multiplied by v minus nb, and this is equal to nRT. This equation is known as van der Waals equation for n moles of gas. Okay, now in this, these constants A and B are called van der Waals constant, and their value depends on the characteristic of a gas. Now this van der Waals equation can also be written for 1 mole. Okay, P plus A by V square, V minus B is equal to RT. This is for 1 mole. Now significance of van der Waals constant. A, this is in pressure term. That's why it represents the magnitude of intermolecular forces of attraction. and this B, this represents the effective size of the molecule, or we can say this represents the excluded volume. Now what is this excluded volume? Again see this diagram. This is the free volume which is available for the gas molecules. Okay, but in this volume, actually the actual volume of the gas particle, like this is not available for gas molecule to move. That's why this is excluded volume. And in this diagram you can again see this excluded volume is determined by this collision diameter. Okay, this is one gas particle and this is the another gas particle, and we can say in this range this is called collision diameter, and that's why this space or this volume, this is excluded volume for real gas, and in we can say according to the calculation this excluded volume is 4 times the actual volume of gas particle. Okay, so this is van der Waals equation. Now conditions under real gases can show ideal behavior. Real gases show ideal behavior when conditions of temperature and pressure are such that the intermolecular forces are practically negligible. Okay, and this when we get this situation, then intermolecular forces are practically negligible. The real gases show ideal behavior when pressure approaches 0 and temperature is very high. In these conditions, we can say at very high temperature and at very low pressure, real gases show ideal behavior. Is that clear? Now, what are the differences between ideal gases and real gases? Ideal gases obey all gas laws under all conditions of temperature and pressure, while real gases obey gas laws only at low pressure and high temperature. The volume occupied by the molecules is negligible as compared to the total volume occupied by the gas. But in case of real gases, the volume occupied by the molecules is not negligible as compared to the total volume of the gas. In case of ideal gas, force of attraction among the molecules are negligible, while in case of real gases, the force of attraction are not negligible at all temperatures and pressure. And ideal gas obey this ideal gas equation, PV is equal to nRT, while real gases obey this van der Waals equation, P plus AN square divided by V square, and this is V minus V is equal to nRT. Okay. Now, compressibility factor. The deviation from ideal behavior can be measured in terms of compressibility factor, which is represented as Z. Now, what is this Z? Z is the ratio of product PV and nRT. Mathematically, we can write Z is equal to PV by nRT. Now, if we draw a plot between pressure and Z, that is compressibility factor. For ideal gas, this is equal to 1. Okay, when this Z is equal to 1 for ideal gas, we will get the ideal gas equation, PV is equal to nRT. Okay, for ideal gas, Z is equal to 1 at all temperatures and pressures. The graph of Z versus P, this one, will be a straight line parallel to pressure axis, this one. And for gases which deviate from ideality, value of Z deviate from unity. That is, for real gases, Z is not equal to 1. It may be less than 1 or it may be more than 1. At very low pressures, all gases shown have Z is almost equal to 1 and behave as ideal gas. We can say that is this condition, when pressure is almost 0, this Z is almost equal to 1. At high pressure, all the gases have Z is greater than 1. That is, as the pressure is increases, for all the gases, this Z is greater than 1. These are more difficult to compress. At intermediate pressure, most gases have Z is less than 1. It is this condition. This one. Okay, less than 1. Thus, gases show ideal behavior when the volume occupied is large, so that the volume of the molecules can be neglected in comparison to it. Boyle temperature. Up to what pressure a gas will follow the ideal gas law depends upon the nature of the gas and its temperature. Okay, the temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called Boyle temperature or Boyle point. At low pressure and high temperature, gases show ideal behavior. Now, what is the significance of Z? For real gas, Z we can write like this. Z is equal to P V real divided by N RT. Now, if the gas shows ideal behavior, then we can write V ideal is equal to N RT by P. Now, see in this equation, this we can say that is this N RT by P. This is equal to V ideal. That's why we have Z is equal to V real divided by V ideal. That's why we can say compressibility factor is the ratio of actual molar volume of a gas, that is V real, to the molar volume of it if it were an ideal gas at that temperature and pressure. Is it clear? Thank you. Subscribe my channel to get the videos of next chapter.